Okay, so we've been doing lots of multiple integrals, and there's one more technique that I want to show you before we move on to the next topic. Here we go. Okay, so the last technique that I want to show you is about doing double integrals in polar coordinates. Let me kind of quickly remind you what polar coordinates are. So let's say you have a point in two-dimensional region. Let's say the coordinates is x comma y. So if you have a point on this coordinate, you can kind of draw like a line from the origin to the point, and then make like a right triangle with the base that's the length of the x coordinate and the y coordinate leading up to the point on the plane. You could describe this point by describing the distance from the origin. So I'm going to call this the radius r, and the angle it makes counterclockwise from the positive x-axis. So whatever this angle is. If it's a negative angle, it goes down clockwise direction from the positive x-axis, and then yeah. So that's how you can describe a point. Using trig, we know that the cosine is the ratio between adjacent side and hypotenuse. So cosine of theta is x over r. Or if you take this equation and multiply both sides by r, you could describe x coordinate by r times the cosine of the angle. And using similar technique, you could describe the y coordinate as r times sine of theta. Another useful identity would be that that x squared plus y squared is equal to r squared. And you could get that from these two equations by squaring both of these equations and adding them, and taking the note that cosine squared plus sine squared equals 1. So if you multiply that by r, you're just going to get multiply that by r squared, you're going to get r squared is equal to x squared plus y squared. Okay, so basically, what I want to describe is u substitution in double integral situation, but this very specific u substitution, this pair. So u substitution is actually way more complicated than it is in one dimension, where you could say u is equal to whatever function of x you like, and then computing this kind of dilation factor, du, is f prime of x dx, as you know. It's a little bit more complicated because you're changing two variables at the same time, and it's actually a little bit out of scope for us. But for this particular case, I still want to describe how this distorts the two-dimensional space. So when we're using variables x and y, you could imagine two-dimensional space being chopped up into rectangular grid, as I did in the drawing before. And I'm gonna think of this as dA. This little area element is the change in x multiplied by change in y. It's a little rectangle, base times height. Okay. When you're doing it in polar coordinates, I want to divide up the region in a mesh like this. So each these area element, it's not quite rectangle. It's kind of like a shape that your windshield wiper in your car sweeps out, right? So imagine these are concentric circles, right? So if you take two very close together radius concentric circles, and you chop this up into equal angles, that's the little area segment you get. So how do we compute this area? Well, let's write out how we would compute that area. So we know that area of the big circle, let's say, is pi r2 squared. Pi r squared is the area of a circle. And then we're going to subtract area of the inside circle. Let's say radius 1. It's going to be pi r1 squared. So what we have so far is this bit. Pi r2 squared minus r1 squared. So that gives the area of annulus, like a donut-shaped region, with r1 and r2. Imagine that being close together radius. And then we're taking this angle that's 2 pi radians around and chopping that up into lots of pieces. So so far, we've computed the area of the full 2 pi radians. So what we could do is we could look at the difference in the angles. So this is angle theta 1 and angle theta 2. And theta 2 minus theta 1 is the difference in the angle out of the full 2 pi radians of the full circle. Okay, so that's the little area that we're looking at. That's the shaded region. Let's simplify this a little bit. Okay, so r2 squared minus r1 squared, this is a difference of squares. So you could actually factor this into r2 plus r1 times, I have this backwards, r2 minus r1. R2 is bigger in this context. And then let's see, the pi cancels because there's a pi that appears on the top and pi that appears in the denominator. We still have the 2 in the bottom though, so I'm gonna leave that as 1/2 in the front. And this is what I have. So 1/2 times r1 plus r2 and r2 minus r1 and theta 2 minus theta 1. Okay, so I'm imagining this r2 minus r1 as dr. That's the small change in the radius. And theta 2 minus theta 1, that's your d theta. That's your small change in the angle. R1 and R2 is some radius from the origin. But as I've said, R1 and R2 are very close together radius. So let's just say halfway in between, we have the radius R. Just to kind of, instead of doing R1 plus R2, I'm going to make up for it by taking the average of the two. And then say the average of R1 and R2, let's call that radius R. But now I have R plus R, which is 2R. And then 2 could cancel with the 2, 1/2 in the front. And what we have is R times change in R times change in theta. So we can think of the area element of this little section that I have there, the windshield wiper section, could be described by r dr d theta. And that's going to be the, I guess, the substitution, like stretching factor, right? So this kind of makes sense because little segment near the origin is smaller than a section further out, and it scales like the radius. Okay. All right. So how does this actually work when you're computing the double integral? So let's say I have the double integral that's described in this way, some function of x and y, and then we're integrating some region R. What we're going to do is every x and y is going to be replaced with, the x is going to be replaced with r cosine theta, and y is going to be replaced with r sine theta. So that's the substitution that's going to be made. And of course, when we change the variable, we distort the grid, but we can make up for it by changing the dA into r d theta. So dr and d theta behaves the way you expect with the integration, but you get an extra factor of r inside of the integral, and that's you don't want to forget that. Okay, so let's kind of do an example of how this might come into play. Okay, so let's say I have this double integral. Okay, and the region R that we're looking at looks like this. So let's see, let me draw it. Okay, y is greater than or equal to 0, so we're looking at the upper half space, so above anything above the x-axis. And then we're looking at x squared plus y squared. So x squared plus y squared equals r squared is going to be a circle of radius r. So on the lower end, the radius is 1. Okay, and on the higher end, the radius is 2. Okay, so we're looking at all the circles of radius between 1 and 2. So that shades in this half a donut region right here. I hope that makes sense. And you can kind of see that this is a really awkward region to integrate using x and y variables. But if you're describing this region in terms of r and theta, it's actually pretty straightforward. The angle is between 0 and pi, and the radius is between 1 and 2. Okay, so these kind of regions that that looks like that has circles in them, and also maybe some kind of rotational symmetry is a hint that maybe you might have an easier time integrating if you do it in polar coordinates. Anyways, let's continue with this integration. So what are we going to do? So every x is going to turn into r cosine theta, and every y is going to turn into r sine theta. So if you square it, it's going to be r squared sine squared. And then dA is going to turn into r times dr times d theta. Okay, and then the inner integral is going to be the dr. So radius is changing from 1 to 2. So those are the lower and upper limits of the integration. And angle theta is changing from 0 to pi. Okay, and that's the what we got over here from the drawing. Okay, so I guess we can integrate this. I think it's a little easier if you broke this up into two integrals. So do this guy and this guy separately. So the first integral, we have cosine theta, but cosine theta doesn't depend on r. So I'm going to pull that outside of the inner integral. The inner integral is going to go from 1 to 2. And we have what's left is 3r, or actually I have to multiply by r. I have to distribute the r to both of these terms. So we're going to have r squared, and 3 is a constant that I can pull all the way in front of both integrals. Okay. For the second integral, I can pull out the 4 all the way out. I can take out sine squared. An angle is changing from 0 to pi. And r, what's left is r cubed. Okay. All right. I don't think I left myself enough room to compute this, but let me go as far as I can. So okay, 3 integral from 0 to pi of cosine theta, and antiderivative of r squared is r cubed over 3, and r is changing from 1 to 2. Okay. And antiderivative of r to the 3 is r to the 4 over 4, and r is changing from 1 to 2. Okay, let's see. So I want to do this integral, but first of all, 3 in the front and 3 in the denominator here could cancel out. And if I plug in 2, I get 2 cubed, which is 8. And if I plug in 1, I'm just going to get 1. So 8 minus 1 is going to be 7. Okay, so 7 times integral of cosine from 0 to pi plus, let's look at the second integral here. So the 4 out in the front and 4 in the denominator, again, cancels out, which is kind of nice. And then what do I have? So 2 to the 4th power, I guess that's it's going to be 16 minus 1 to the 4th power is 1. So 16 minus 1 is 15. I'm going to pull that constant out. And I want to integrate sine squared. So sine squared, we can integrate it by using the double angle. Right? So 1 minus cosine 2 theta all over 2 d theta. Man, I'm running out of room. Maybe I can make it. Okay, so antiderivative of cosine theta is sine theta. So 7 sine theta from 0 to pi. Okay, so sine of pi is 0 and sine of 0 is 0. So the first integral will work out to be 0. And I'm going to pull the 1/2 into the front and have 15 over 2 in the front. Okay, antiderivative of 1 is just theta, and minus antiderivative of cosine 2 theta is sine 2 theta over 2, and theta is changing from 0 to pi. Okay, let's see. Let's look at this sine 2 theta part. So sine of 2 pi and sine of 0 is again both 0. So this term just kind of dies out. But theta is changing from 0 to pi. So that's going to be pi. So 15 over 2 times pi. Okay. I barely fitted it in. Okay. So we were able to compute the integral. So yeah, the trig integral might have been a little bit trickier than integrating this with expected x and y. But if you actually look at the region, describing this region, cutting it up into top and bottom curve and setting it up that way, it would require much more tedious computation. So overall, polar coordinate computation is actually easier here. Okay, and it's not just sometimes it's easier. Sometimes you can solve problem that you could not have done with x and y coordinates. Let me show you an example here. So the integral I want to show, it's an improper integral from going from negative infinity to infinity. of e to the negative x squared. So depending on the calculus instructor you've had for calculus 2, you might have learned that some integrals are impossible to do. And this is one of those guys. So the graph of e to the minus x squared looks something like this. And this might be a curve you've seen if you've taken a statistics course. This is the bell curve, or something very similar to a bell curve. So if you've seen a normal distribution or bell curve in statistics course, the curve itself isn't quite that, but it's very close. It's this function multiplied by a constant, which is stretched or shrunk, and then shifted to the left or right. But essentially, basically, this is the curve we're looking at. And when you're doing probability or statistics, we want to compute area beneath the curve. So that corresponds to probability that a certain variable will be within a certain interval. Okay, and so this would be a very useful function to be able to integrate, but none of the techniques in Calc 2 work. It's actually still impossible to compute the area exactly from two numbers a to b. But if you want to integrate from negative infinity to positive infinity, it's actually doable. But you kind of artificially use double integral. And let me show you how. This is a really cool trick. Okay, so the trick is I want to compute this integral. But instead of computing this integral, I'm going to compute the square of this integral. So I'm looking at the square of this integral. And when I integrate, like x is just a dummy variable. So I could have named the variable anything I want. I could have named it x, I could have named it y, I could have named it w, it doesn't really matter. So these two integrals, I'm going to use the variable x and variable y. Okay, exact same integral, I just changed the label by a different variable name. Okay, so now I have two integrals. I have this integral and this integral. And since x is constant with respect to y, what I'm going to do is I'm going to put this inside of this integral. So I have e to the negative x squared times e to the negative y squared. And if I'm multiplying two exponential functions with the same base e, that's the same thing as adding the exponents together. So that's going to be the new integrand, e to the power of negative x squared minus y squared, and it's dx dy. This is the integration I'm doing. Then now I'm going to convert this to polar coordinates. So what am I integrating? Well, I'm integrating x and y both from negative infinity to infinity. So that's everything on the plane, xy plane. So if I describe this in polar coordinates, so the radius is going from 0, from the origin, off to infinity. So integration is going to go from 0 to infinity. And all the angles, so 0 to 2 pi. Okay. And remember that x squared plus y squared is equal to r squared. So negative x squared minus y squared is going to be negative r squared. And that's a simpler expression to integrate. So that becomes the new integrand. And then dx dy is going to turn into r dr d theta. So we'll get an extra factor of r because we're integrating with respect to in polar coordinates. Okay, so now how do we integrate this? Well, we're going to integrate this one at a time with respect to r and then with respect to theta. When we're looking at the integration with respect to r, we're going to do a u substitution. U is equal to negative r squared. So I'm doing one-dimensional version of the u substitution. So du is going to be negative 2r dr. And because we're doing this in polar coordinates, look, because we have this extra r that comes from polar coordinates, we could actually compute the u substitution. So if we were doing this problem and try to do u substitution with negative x squared, we would not be able to compute the u substitution because there's no x to take away. But because we have this extra r, we could do the rdr is same thing as du. And we have rdr here, which is going to turn into du. And I know there's a negative 2, so we have to make up for it by dividing by negative 2 in the front. Okay. Now let's integrate. We have this weird thing where we have to also update the limits of integration. R is changing from 0 to infinity. So if r is equal to 0, u is also equal to 0. So 0 stays 0. But if r is blowing up to infinity, negative r squared is going to blow up to negative infinity. So the upper limit is going to change to negative infinity. We have this weird thing where the upper limit is smaller than the lower limit. So we're going to flip it. We're going to bring the negative infinity below here and 0 up here. And whenever you switch the limits, you can make up for it by putting a negative sign in front, or if there already is a negative sign, we can just take it away to make it positive 1/2 in front. Okay. All right, now it's starting to look like something that we can compute because antiderivative of e to the u is just e to the u. Okay. And u is changing from negative infinity to 0. So let's just look at the graph of e to the u. Okay. If you go to negative infinity, it gets closer and closer to 0. And e to the 0 is that anything to the 0th power is at 1. So e to the 0 is 1, and we're going to subtract 0 from it. So this, after the integration, we just have the constant 1. So that's what we have now. And antiderivative of 1 is just theta with respect to theta. So 1 turns into just theta, and theta is changing from 0 to 2 pi. So we have 2 pi over 2 or just pi. Such a beautiful answer to a really cool trick. So what does this mean? The original integral is equal to square root of pi, because what we actually computed was the square of the integration that we wanted. So this integral is square root of pi. Okay, that was a really cool trick, right? This is my favorite integration technique of all time. It doesn't get used very frequently, but I thought it was really neat. Okay, anyways, we haven't talked about how to do, in general, how to change the variables with double integrals or higher dimensional version of these, like triple integrals and quadruple integrals. Like if you have high dimensions, how do you change of variables? That is out of scope for this class, but if you want to learn, there's a class that you can take. It's TMath 324 Advanced Multivariable Calculus course. In Tacoma, it's usually offered in fall. So if you're inclined to take more calculus and learning more of these advanced techniques, that's where you can learn how to do change of variables. Okay, I think this is a good place to stop. So I'm going to stop recording. I'll see you guys later.